Okay, so today we're going to be talking about nuclear decay reactions, and specifically balancing nuclear decay reactions. We are going to get a lot more in depth into nuclear after the semester is over, but since we were talking about chemical reactions and balancing chemical reactions right now, I wanted to talk about balancing nuclear reactions as well. It fits in nicely. So the first thing we need to briefly talk about is the fact that there are 4 different reaction types that we're going to be looking at here. There's alpha radiation, which is a helium nucleus, beta radiation, which is an electron, gamma radiation, which is just straight energy, and then neutron radiation, which is obviously just a neutron. And so different types of elements are going to undergo different types of radioactive decay. Whenever something becomes unstable, it needs to undergo radioactive decay in order to gain stability. And so it's going to release one of these 4 types of radiation types in order to reach that stability that it needs to reach, whether it needs to lose 2 protons and 2 neutrons in the form of a helium nucleus like an alpha particle, or lose an electron like a beta radiation, or lose just energy like gamma, or lose a neutron as a neutron radiation. It doesn't matter. It's going to do that and become stable, but we need to be able to balance that. Now, chemical reactions, I've told you from the get-go that chemical reactions, we cannot change the actual chemical itself, because doing so would change the chemical and not make the reaction that we're talking about. Now, nuclear reaction and balancing nuclear reactions, we are actually changing the chemical, because we're changing the nucleus, which means we're changing the chemical. We're altering that fundamental principle of what makes up an atom. And so that is going on here. So this is not a chemical reaction. It is a nuclear reaction. It's on the subatomic level. We're talking about protons, neutrons, and electrons here. So do keep that in mind. You can't really lump these together, but in terms of balancing, we can. So alpha decay, it's when an unstable nucleus emits a helium nucleus or an alpha particle and decays into a new stable nucleus. So for example, platinum-175 will alpha decay and become osmium-171 and emit that helium nucleus. Now you'll notice here the key thing with these is that our numbers need to stay the same, because we cannot, while we are altering the type of atom that we're talking about, we can't create or destroy matter. So the number of protons and neutrons still has to be the same. So the total number on top, our number of protons and neutrons, that mass number has to be the same. We have 175 nuclear particles on the left. We need to have 175 nuclear particles on the right. 171 plus 4 is 175. If we have 78 protons on the left, we need to have 78 protons on the right. 76 plus 2. I will not be expecting you to look at an element and understand or predict what type of radiation it's going to undergo. What I want you to be able to do is identify different types of radiation decay, what they are, and balance these types of reactions. If I told you that platinum was going to alpha decay, I need you to understand and be able to predict the fact that it will make osmium. And it's all based on the number of protons that you're losing. If I look at the periodic table, if I lose 2 protons due to alpha decay, I go from 78 down to 76, which platinum is 78 and osmium is 76, so it has to be osmium. And we'll go through this in class as well. So there's that alpha decay right there, is that helium nucleus, and it has to be a part of the reaction so that we can maintain that mass, that same number of nuclear particles. Now beta decay happens when an unstable nucleus converts a neutron into a proton and an electron. So a neutron, something that's neutrally charged, is going to be converted into proton and an electron, a positive and negative charge. So we keep that overall neutrality, but we create a new proton and an electron. The proton remains in the new stable nucleus, but the electron is ejected. So that's where the beta, that electron, is the radiation that's going out. So now we're taking lithium, which has 8 protons and neutrons, 3 of those being protons, and we're making one of those neutrons, so one of these 8 is going to become a proton and an electron. So 8's going to stay the same, but 3 is going to go up by 1 because we're going to create a proton, making 8 and 4. And so then in order for our bottom number to stay the same, in order for that proton number to stay the same, we have to have 3 and then 4 minus 1 is also 3. So it's all just about keeping those numbers balanced. And having 4 protons means that we are beryllium. And there's that beta particle. Now, gamma decay is not a form of mass. It's just an unstable nucleus emitting energy as a gamma ray to stabilize the nucleus. So something like cobalt-60 will release gamma rays. Now, it stays cobalt-60 because we did not change the number of protons and neutrons. So the element itself stays the same. It's just releasing extra energy in the form of gamma radiation. And then we've got neutron decay, where a neutron decay reaction occurs spontaneously or due to fission, and we'll get into more detail on that when we do our nuclear chemistry unit. But right now what you need to know is that californium will decay into 2 smaller particles, releasing more neutrons. And so in something like this, on a test I might ask you to, I would give you maybe the californium and xenon and ask you to predict what the ruthenium and neutrons, how many neutrons are left. I'd probably give you how many neutrons, but you'd have to tell me what the number here is. Is it 10 or 01? So what we're getting into now is just very purely simplified nuclear reactions, just that we're looking at balancing those numbers. The tricky part is when we're going to do next, which is, that's a neutron, which is the nuclear decay series. And what's going on there is that sometimes one decay is not enough in order for an atom to become stable. Sometimes these atoms are so unstable that just one decay is not enough. They decay into something that also is unstable, and so they'll have to undergo something called the nuclear decay series. It will continue to decay until it reaches a stable nucleus. Now, I will never ask you to memorize the nuclear decay series, but I will ask you to fill in the blanks. And so decay series show the different transformations of an unstable nucleus in order to reach stability. And so something like this, where uranium is going to decay through various different reactions down to stability of lead-206, it's going to undergo alpha decay from uranium-238 to thorium-234, then beta to protactinium 234 down to uranium-234 down to thorium-230 down to oh my gosh, I don't know why my brain is radium-226 down to radon-222 down to polonium-218 down to lead-214 it'll beta down to bismuth-214, which beta is into polonium-214, which alpha is into lead-210, which beta is into bismuth-210, which beta is into polonium-210, which alpha is into lead-206, which is stable. So I would never ask you to predict a decay series, but I might ask you to fill in the blanks on one. And different isotopes and different elements have different decay series, and these are things that are known and that we study and look at in the nuclear chemistry world. So this again is just a brief overview of what we're going to be doing. Right now we're just focusing on balancing those reactions. We'll get into the idea of nuclear chemistry and the nitty-gritty behind that after the semester. So come ready to work tomorrow. Thanks, guys.